Good morning, ninth grade. Today we're going to be talking about transferring charges, and so let's just jump into it. Now, last time we talked about static electricity and charges and things like that. We didn't really get into how exactly we transfer that charge, and there are two main ways we can transfer charge, and there's a lot of different things you can do with them. We're going to talk about just some of them today. So first thing we have here is this idea of sharing a charge. Now, when a charge is shared through direct contact, as we see here, it is called conduction. And so when you have a direct contact with the other object, you have conduction. And so let's look here at this diagram. You can see some conduction going on here. So first we start with the charged ball. Now you can see it's full of negative electrons or negative charge. So what happens here is he's got it and it's full, and then he hits this neutral rod and those electrons go into the rod, and then he leaves and the electrons are still in the rod, and both objects are now permanently charged. And so that's what's going on here. You can actually pause this and take a look at it if you want to, and really just take this in and see what's going on. Electrons, they travel to the rod and they do not leave. This is actually a permanent thing. We're going to talk more about that in the next slide here. A charge imparted by conduction has the same sign, positive or negative, as the original charge. So we can look back and we can see this right here. You can see that the ball was negative, and then it hit the rod, and the rod was neutral before, but now the rod is also negative. And so now they are both negatively charged, which proves a point here. Charge by conduction has the same sign, positive or negative, as the original charge. So that's one way we can see that. The next thing we see here is because electrons physically move from one object to another, charging by conduction is permanent. And we talked about that before as well. You can see it in the diagram. In the example from before, the rod stays charged even after the ball is gone. And in case you need to see that again, let me just pop over here, and you can see it. The rod does not lose its charge, even though all the electrons do spread out a bit. They start out very close. Let me see right here. And then, go away. Give it a second. And then it just spreads out throughout that rod. It doesn't really go anywhere. It does not leave. But we're going to see certain scenarios, it kind of looks like it leaves, or it acts kind of like it leaves. See, in humid air, very much like Florida, this can actually cause the charge to leak into the atmosphere. And so static electricity is not very well transferred, even by conduction, when there's a lot of humidity, because it's very easy to lose your charge in humidity. Now, the cool trick is that most libraries are actually not humid at all. They have to stay very dry because they need to make sure the pages on the books don't mold or mildew. And so what they'll actually do is they'll have a dehumidifier running the whole time. This makes it so that you can actually very easily shock people in libraries. Usually libraries also have very nice carpet, so that also helps with shocking people. So just something to know to annoy your friends and things like that. Now from here, see, I'll move. There we go. Now we also have to deal with the law of conservation of charge. And this law states that charge is the same both before and after an interaction. And so let's say that we had 10 coulombs in this ball right here, as you can see, and the rod is neutral, so it has 0 coulombs either way. Well, when the rod and the ball make contact, what happens here is that now the charge is split between the two of them. And so now the rod has 5 coulombs and the ball has 5 coulombs. But in this case, we can see that the charge was the same before and after. Before it was 0 plus 10, which is 10, and then after it was 5 plus 5, which is 10. And so that is the law of conservation of charge, and it's very important to see that there. It's a pretty simple concept when it's laid out like this, so you may want to pause and think about it, or maybe watch this section over again if you didn't get it for sure. Now from here we go on to this idea of grounding. Now when you get grounded, you get sent to your room because you did something silly. When electricity gets grounded, it's a whole different scenario. Right here, an object's charge can be removed by bringing it in contact with the ground. Okay, well, why? Why is that? You know, why is it that I can put this electrical object in the ground and then suddenly the charge looks like it's gone? Well, it's because the Earth is so large, it can actually absorb a lot of an object's charge with little change to its own charge. And so, since we have such a big planet that we're on right now, it doesn't even look like the Earth's charge is changed when you put a whole bunch of coulombs into it. And so that's probably the safest and best way to get rid of a whole lot of charge. Unless you're dealing with something insane, grounding an object is the easiest way to get rid of charges. Now, the process of diverting unwanted charge to the Earth is called grounding. So I guess I didn't say that before, but that basically is what is going on here. Now you can see an example at the bottom of this page here of somebody actually grounding an object. And so the first example on the left is grounding a negatively charged object. And so that ball had a lot of negative charge in it, and when it hits the ground, that all gets dispersed in the ground, and we could assume eventually all of it would be gone, probably very quickly. It doesn't take very long for static electricity to go. Now for positive charge, it's a bit more interesting. What actually happens here is that electrons from the ground will actually go up to neutralize that charge. When you use negative charge, it actually just spreads out throughout the Earth. When you ground a positive charge, it actually just absorbs electrons from the Earth that it has. But either way, since the Earth is so massive and has so many electrons just running around in it, it doesn't even look like it changes the Earth's actual charge at all. It's so small compared to the giant Earth that we live on here. So that's how grounding works. Now from here, we are going to talk about this idea of inducing a charge. Now, without direct contact between objects, objects can be charged in the process known as induction. And so induction is without direct contact. That is in stark contrast to conduction, which you need a direct contact. So let's look at this diagram and try to figure out what's going on here. So we see a negatively charged ball on your right. This guy right here, he's holding it, and it's got a lot of negative. So before it even gets to the pole, or the rod in this case, it will actually induce a positive charge that is attracted to the negative charge of the ball that the guy is holding in there, because we've learned opposites attract, and so the positive is actually drawn toward the negative ball here. Now, at the same time that opposites attract, we also get another thing going on, which is like repel. So those like charges are actually repelling each other. So at the same time that the positive charge goes towards one end to try and meet up with the negative charge that has not touched it yet, it's just in the air between it, all of the electrons and the negative charge force the electrons in the rod to go the opposite direction. Therefore, it is then induced. And so that's pretty cool there. Now, after you move the rod away, well, after you move the ball away, as you see in the last panel here, the third one, it'll actually just neutralize. And so this, for the most part, is temporary, as we're going to see here, induction. Charging by induction produces two charges instead of just one, and we can see that once again right here. we have a positive end in the middle. So the middle example, this one right here, we have a positive and we have a negative. And so it actually makes two different charges instead of just one with conduction. Now from there, charging by induction is usually temporary, and we saw that once again right here. After the ball moves away, then the charge just goes back to normal, and the electrons just go back to where they normally are. But also, both induction and conduction still obey the law of conservation of charge. So that is something else to know here. Even though it may not seem that way, they actually do. Now, even though induction is usually temporary, it can be made permanent by combining it with grounding. And so this is what you would have to do in this sense to permanently charge an object through grounding. So you have the charged ball once again, and we have the neutral rod. Well, you start the induction, and then you have somebody else put their finger on the end of the rod that's being charged. That, in a sense, will actually ground it. And when it grounds it, the rod will actually become positively charged, not negatively charged, because all the electrons, as you can see here, they go from the middle and they actually go toward this guy's hand, and so the electrons have a place to go, and then they'll eventually escape into the ground. This means that the rod at the end is now positively charged, and so it has no electrons, so it stays positively charged, and it will not change unless something else is going to happen to it. Something has to happen for it to change. This process right here that you see here is permanent, and it's even something that you can do to a certain extent. Now, that is the end of what we were talking about today. Hope you guys have a wonderful day. Make sure to take those notes and send them to me for your assignment for today. Thank you very much for listening, and I hope you have a wonderful Wednesday. Goodbye.